Welcome to Yaka Digital Network. If you look at this 2D orthographic drawing of a Boda engine block, it is almost impossible to read. The internal mechanics are completely buried under dozens of overlapping dashed hidden lines. We solve this by using a technique called sectioning. Imagine a sheet of glass, a cutting plane, slicing straight through the object. Immediately, those chaotic dashed lines disappear, replaced by visible, solid boundaries showing the exact internal cavities. By virtually cutting the object open on paper, you translate a cluttered blueprint into clear instructions that a manufacturer can actually build from. Let's apply this to a simpler object. This is a hollow metal bracket. When our cutting plane passes completely through the entire length of the part, we create what is called a full section. On the drawing, we mark the exact location of the cut using a cutting plane line. Notice the specific pattern, one long dash followed by two short dashes, drawn with a thick line weight. The bold arrows at the ends point in the direction the observer is looking after the cut is made. Next, we map the areas where the imaginary knife sliced through solid material. We do this using hatching. These are thin, evenly spaced diagonal lines drawn at a 45-degree angle. Notice that the hollow center remains completely blank. Hatching operates as a formal language in engineering drafting, giving technicians an immediate visual cue to differentiate solid mass from empty space. Many mechanical parts, like a standard maze mill pulley, are perfectly symmetrical. Slicing a symmetrical object repeats the same information. Instead, we use a half section, removing 1/4 of the object. On the 2D drawing, the center line acts as a strict border. The left side displays the exterior, while the right reveals the hatched interior. This method optimizes your drafting space. You successfully communicate both the outside dimensions and the inside cavities in a single, efficient view. Things get slightly more complicated when you section an assembly, where multiple separate parts are fitted together. Here we have a gear sitting inside a mechanical housing. If we hatched both of these adjacent parts at the exact same angle, they would visually merge into one solid block of metal. To prevent this confusion, we must alternate our hatching angles. First, we hatch the housing at the standard 45 degrees. Then, for the adjacent gear, we flip the hatching to an opposing angle, typically 135 degrees. Those alternating angles create a sharp visual boundary, ensuring the reader knows exactly where one component ends and the next begins. Now look closely at the center of this assembly. We have a solid central steel shaft holding the gear in place, and a thin structural web supporting the housing. Both have technically been sliced by our cutting plane. Here is a challenge. Based on engineering logic, which of these specific parts should remain unhatched on your final drawing? You have 5 seconds. Correct. The steel shaft remains unhatched. Standard solid hardware is never hatched, keeping its shape obvious. You also leave the web unhatched. If you hatch a longitudinally cut thin rib, it falsely appears as a thick, massive, solid block. Knowing exactly what to exclude from your hatching proves to an examiner that you understand the true physical structure of the parts, rather than just blindly applying lines to a page. Let's review our finalized assembly drawing, anchored by its cutting plane label. Line weights are strictly maintained, thick for the cutting plane, thin for the hatching. We applied opposing angles for adjacent components and left the central shaft and web solid. Executing these specific details flawlessly is what UNEB examiners demand to verify your technical drawing competency. Take a screenshot of this summary graphic now. It contains the strict sectioning rules you need to memorize for your upcoming exams. Thank you for learning with Yaka Digital Network. You can watch more videos for all classes here and get all content at www.yaka.cc. Following these standards ensures your blueprints translate perfectly from the drafting board to the workshop floor.